Whoa! We are back, and today we're going to be talking about properties of functions. Be more specific, even and odd functions. Determine whether or not a function is even or odd. So let's look at this right here. Boom. You see that red line? Yeah. That's letting us know that even functions are symmetric to the y-axis. Even functions are symmetric to the y-axis. All right? And then this red dot, that's letting us know that odd functions are symmetric to the origin. You can be symmetric to the origin across these diagonals. That's what happens with the origin. All right? But they must look the exact same on opposite sides in that diagonal. All right, let's just go ahead and move forward and jump into this. You can read the theorem, but the theorem is just basically going to say what we scribbled on the image there. Determine whether each graph is given as an even function, odd function, or neither. All right, I'm gonna look at this. Boom. All right. Oh, we got some action that looks the exact same on each side of the y-axis, and if it's looking the exact same on each side of the y-axis, then it is going to be an even function. Even because symmetric to the y-axis. All right. Now look at this middle one. It doesn't look like a mirror on the left and right of the y-axis. Yet it doesn't look like you can look down in the pond for it to be symmetric to the x-axis. And it has no action that's showing the same stuff happening on opposite sides of those diagonals go across the origin. So this is a definite neither. And boom, look at that action through that origin. Draw a diagonal. Boom, looking good. Same on that diagonal. All right, boom. Clearly, if it's an odd function, if it's symmetric to the origin. Odd because symmetric to the origin. So, boom. All right, let's keep rolling. All right, we need to put some stuff back in here. This is missing a few things. All right. Now, it says identify even and odd functions algebraically. There's a little thing that I do, and it's just my way of running my test to determine if a function is even, odd, or neither. And so, the layout for this, if I plug in negative x, and there is no sign change, that's telling me that my function is even. No sign change means my function is an even function. If I plug in negative x and there is a total sign change, then that function is an odd function. But it got to change all the way, 100% change. But then if there's a partial change, hey, don't nobody want no partial. Either you all in or you don't change at all. Partial change, neither. And I should say partial sign change. All right, so no sign change or total sign change. But you have to test that negative x on your function. So let's plug negative x into our function and see what we get. So we plug in negative x, and after simplification, we have negative x cubed minus 5x. All of the signs changed. Since all of the signs changed, that is a total sign change. So that lets me know that I have myself an odd function. And just for a little extra gravy on my mashed potatoes, I'm going to say it's odd and it's symmetric to the origin. Let's put in this information that's missing here. All right, remember, no sign change. Oh, that looks so ugly. Let me clean that up. No sign change. You have an even function. Total sign change. You have an odd function. Partial. Don't nobody want nobody being partial. So you have neither even or odd. All right, so let's look at this one. Run the test. We're going to plug in negative x equals 2 times negative x squared minus 3 equal 2x squared minus 3. Everything looks exactly like the original, no sign change. Therefore, this is an even function. Even function. You know what I'm saying? And just to make sure my grits are rich, I'm going to go ahead and add a little cheese in this thing and say it's an even function and it's symmetric to the y-axis. Okay. Now, boom, equals. I want y'all to run that test. I want y'all to run this test. And when you run this test, it's going to let you know that this is a partial. And that's going to be neither. Neither symmetric to the, neither odd, neither even. Neither even or odd. Anyways. All right, so on this piece right here, right, it says determine where a function is increasing, decreasing, or constant. There are 3 slides for this, but we're going to do it all on this one slide because I like to mark up the slide. All right. If a function is increasing, it is rising from left to right. If a function is decreasing, it falls from left to right. If the function is constant, there's no incline, no decline, just horizontal. So, and all of these are with respect to the x-axis, they're intervals. So, I'm just gonna draw my lines on here. Right there, that's where I got a constant. So I'm gonna draw my line right there and I'm gonna put me a little C right there. And then working up, okay, I'm decreasing right here. And then I decrease again over here. And I'm gonna go ahead and put a D right there, put a D right there for decrease. And then I am increasing until I get to that location. Now I've covered every directional change on this graph. Now all I have to do is put in the intervals. All right, starting with this increasing interval. All the interior points get parentheses. It started increasing at x equal -4, and it stopped increasing when x became 0. And then it was constant when x was 0, and it was no longer constant when x became 3. And the graph was decreasing. All right, notice we're at an endpoint, so we're going to put a bracket on this endpoint at x equal -6 and it decreased until x became -4, parenthesis there, and then it started decreasing again at x equal 3 until it got to +6. +6 is at an endpoint, so we put a bracket on that. Okay, let's keep rolling. And I told you, like before, there's 3 slides that was supposed to take place on, but I wanted you to see it happen in real time. So we'll move on to the next. Finally, we get to the average rate of change. Oh, well, it's not that dramatic. But anyways, all it is the slope in functional notation. B and A are inputs. Remember from a previous section talking about functions, all of your x values are inputs. So in this case, B and A would be x values, f of B and f of A would be y values. Average rate of change is the change in y over the change in x. This delta, that triangle is a delta, and it stands for change in. Change in, okay? Change in. So if it's a y that follows it, that would be a change in y. Let's do an example. It's really easy. All right, so I'm going to set this up for you. You have your inputs and you have your outputs. Equals 3x squared. The function was 3x squared. It says, find the average rate of change from 1 to 3. So I input a 1. I input 1 into that function, and I get out the value of 3. I input 3 into that function, and I get out the value of 27. Notice I didn't try to put any of the numbers that happen between 1 and 3. You only use those 2 values that you're given. And they create a point. They create points. Okay, so 1 created the point 1,3. 3 created the point 327. Average rate of change. Change in the y values. You have 27 minus 3 over the change in the x values. 3 minus 1 equals 24 over 2 equals 12. So the average rate of change is 12 changes in y for every 1 change in x. Now that helps you to see the average rate of change is nothing but a slope once you saw it with these point notations here. All right, math people, we'll be back next time with more math stuff.